Hello everyone, I'm Eleonora Bianchi and I'm a postdoc at the Université Grenoble, and I'm very happy to present you the first results of the FAUST Large Program. So as you can see, FAUST stands for 50 AU Chemistry of the Disk Envelope System of Solar-like Protostars, and in my talk I will give you first an overview of this ALMA Large Program, and then I will focus on the first results that we obtained towards the Class 1 protostar L1551 IRS5. So, FAUST is the first ALMA Large Program entirely dedicated to astrochemistry. It is a very broad collaboration involving Japan, Europe, and the US. And the main goal is to characterize the chemical diversity in the different physical components of Sun-like Class 0 and Class 1 protostars. We know that the planet formation could begin earlier than what was previously thought. So it is important to study the chemical complexity of the early stages to understand what are the initial conditions when the planets start to form. We want to understand if the molecular complexity is at least partially inherited from these early stages, and if the diversity observed in the planetary system is already present at the protostellar stage. To do so, FAUST observed 13 protostars with a uniform angular resolution and sensitivity in several molecular tracers, to prove firstly the different physical components of the system, so from the large scale envelope to the centrifugal barrier, which is the boundary region between the infalling envelope and the Keplerian disk, and the inner disk at a solar system scale, so until 50 AU. FAUST also observed the complex organic molecules and other tracers to prove the gas ionization and the molecular deuteration. Here you can see a more detailed list of the targets, which are all nearby sources located in different star-forming regions. They have been chosen to be representative of the chemical diversity. So, for example, there are well-known warm carbon chain chemistry sources like L1527, well-known corinos like IRS4A, and other intermediate situations. Each source will be observed in 3 setups, in band 6 and band 3, and in 3 different array configurations to recover from the large scales, so around 200 AU, until the small scales, around 50 AU. And the observations are almost completed. And I would like to stress the huge work done by the FAUST data reduction team, who discovered a visibility amplitude calibration error in the ALMA observation for sources containing very strong lines or continuum emission. So they developed an additional calibration routine to correct for this problem. And if you are interested, I invite you to check the dedicated page in the ALMA Science website. So after this general overview, I will talk you about the first results we obtained toward the Class 1 protostar L1551 IRS5. This is a very well-studied source composed by a binary system and a circumbinary disk. Both the northern and the southern component show emission from protostellar jets, and also an infalling rotating envelope was observed using the CS emission. And this is the FAUST view of the system. So the main results of this work is that we discover a hot corino in the inner region of the system. In the first panel, you can see the continuum emission, where there are indicated the position of the northern and the southern protostars in the different years, since in this system we can observe the proper motion. And the arrows indicate the jet directions. In the other panels, you see the emission from interstellar complex organic molecules, such as methanol, deuterated methanol, methyl formate, and ethanol. As you can see from the maps, we are observing a spatial scales comparable to our solar system. And the ICOMS emission seems to be associated more to the northern source, even if a contribution from the southern source cannot be excluded with the present angular resolution. So on the right, you can see the spectra of methanol extracted in the different position, indicated with the small squares in the methanol map. So from P1 to P8. And in particular, the P3 position corresponds to the continuum peak of the northern source, while the P6 position corresponds to the continuum peak of the southern source. And again, also from the spectra, you can see that the emission is brighter toward the north, and also the spectra shows a double peak profile. So we can conclude that the northern source is for sure a hot corino, and for the analysis, we extracted the spectra at the continuum position of this northern protostar. The first thing you will notice is that the source is extremely line-rich, and we could identify several transitions of this complex species, such as methanol, 13-methanol, deuterated methanol, methylformate, and ethanol, covering a broad range of upper-level energies. So, to derive the gas properties, we perform a non-LTE large velocity gradient analysis of the methanol lines, and we could derive the gas temperature of around 100 Kelvin and a large density larger than 10 to the 8 centimeters to the minus 3. We derive for the emission a compact size of 20 AU in agreement with the hot corino origin of the emission. We found also that the methanol emission is very optically thick. In fact, even the 13 isotopolo has an opacity larger than 2. For deuterated methanol, methylformate, and ethanol, we perform a rotational diagram analysis to derive the species column densities. Note that probably also the deuterated methanol is optically thick, so the measured methanol deuteration is not really reliable, while the emission from methylformate and ethanol is optically thin at these conditions. So the main take-home messages from this work are, first of all, the discovery of a hot corino in the class 1 source L1551 IRS5, which is the third observed hot corino around an evolved class 1 protostar. Then we found that even in an evolved protostar, which we expect to be less embedded, the methanol emission can be optically thick. So we have to be careful to use methanol as a reference when we compare the molecular abundances. Finally, the ICOMS emission is optically thin, so we use the ratio between methylformate and ethanol to compare the molecular complexity observed in this protostar with other younger class 0 protostar, with also the class 1 protostar SBS13A and the protostellar shock L1551B1. And as you can see in the plot on the left, the abundance ratio seems not to vary significantly in the different objects. So we can conclude that globally the molecular complexity do not vary too much from the early class 0 phase to the later class 1 stage. And thanks a lot for your attention, and stay tuned because other exciting results from the FAUST large program will come very soon. Bye bye.